get into all the material. Now, normally, I always try to review what I did last time, but what I did last time was this, so there's not much. And see how the pen gets darker over time? So I need a new pen about every 2 weeks, so it always takes 1 or 2 days before it gets darker. And my handwriting will improve again. And so this is what we did last time, and hopefully you are just kind of bored thinking this class is way stupider than you thought. That's because I'm going easy on you now, or what I meant yesterday, and today that is. So we're going to do much harder stuff. Okay, so again, high school level. Now there's 2 things about this. Now I said that there's a graduate school level way of deriving this. Obviously I'm not going to do that. It is pretty difficult. What we did was the phenomenological way. Let me tell you something about the graduate school way of doing it. Just let me tell you the stipulations. And that is that the gas has no volume. Okay, it means the gas molecules have no volume, and they do not, and there's no interaction between the gas molecules. If you do that, and then you do some graduate school level tricks, you can derive PV equals nRT. Okay, let me back up. I shouldn't have started that way. Let me ask you this. Okay, hopefully you saw this in high school. And they said it's the perfect gas law or the ideal gas equation. I've seen both anyway. Did you think that that was completely 100% accurate for all gases? Huh? Yes, no? No, hopefully not. Now, for one, does it apply to all gases? Well, see, now actually the answer would be yes, because there's nothing in there to identify a gas, right? There's not like, this is the gas constant for helium, and this is the gas constant for hydrogen. Right, so actually this does apply to all gases. But now that already sets me off because I know some gases in a balloon float and some float and some fall to the bottom, right? Other gases will explode in the presence of air if they mix with oxygen. So I'm thinking that that inherently is wrong, that there are a wide variety of gas behaviors, especially helium that floats and something like SF6 which sinks. So something tells me this isn't right because it describes all gases as equal because, again, there's no gas constant for helium versus SF6. And that seems wrong. All right, here's the second way I know that there's something not right about this. Do you think it applies to a gas when it's under incredible pressure? Let's put a balloon and put it in the center of the sun. And it's a Superman's balloon, okay? It can survive the center of the sun. Is PV equals nRT going to work under those pressures? I doubt it because it ought to, what? Is it still a gas? If I pressurize a gas enough, what happens? It becomes a liquid, all right? But this doesn't say that, right? So, it's right, and as you had said, yeah, I don't think it was perfect, and no, it should be. Now, my point here is that, especially on the second example, if I give you an example like this on the test, a question like this on the test, you're allowed to think of extremes. And the extremes might be, well, okay, here's an equation, but if the temperature was 1,000 degrees, or a million, or a billion, or infinity, then something would be wrong. That would be the correct answer. That's the correct way to think about this stuff. You're allowed to put in extremes. If the equation's right, it'll handle it. If it's wrong, like this one, it won't. Okay, anyway, blah, blah, blah. I'm already behind schedule, so let me point out perfect gas behavior with this isochore. This isochore. Come on, you already got isotherm, right? Isochores have constant volume. Okay, occasionally I will intentionally say things that are wrong, waiting you to go, no, you, but you didn't. Strike one. Anyway, we have a quiz. What's an isochore? What's an anyway? All right. So notice I'm doing 1 over x type of behavior because p times v is equal to a constant proportional to t. Charles is well on all that. And again, this is an ideal or perfect gas, whatever, and it can't be right. Let me show you what actual behavior when a real gas looks something like. It does stuff like this. And, if you don't even draw this, that's fine. I'm going to put this up a couple of times. But anyway, here's the idea. Real gases have curves, right? Sound familiar? And so, what? It's okay. And so PV equals nRT does not get that exactly right. Again, the 1 over x, the dark line, as I tried to draw it like perfectly, but I can't draw a perfect circle, is PV equals nRT. I'll just tell you here's the real data of the dashed line. All right, so now what we want to do is take into account that behavior. So instead of a perfect gas or an ideal gas, we're going to do a real gas. Real gases. All right, now, here is a fairly famous way of dealing with this, which is to come up with different equations that have curves, essentially. And here's a famous one. This is called the Virial. And I forgot what the name means something. I don't quite remember. And what this is a Taylor series. Okay, so what it does is it says PV is equal to nRT, so it's looking familiar. Okay, but then there's a Taylor series expansion. And there's these constants that are actually temperature dependent. And so anyway, the constants are of course material specific, and they are, actually generally people stop after the C term, so I've got 3 terms in this expansion. PV equals nRT, and then these are like correction factors that are like a Taylor series, where instead of expanding, 1 plus x squared plus x cubed, I need to be divided by 2, divided by 6, anyway. Instead I've expanded in 1 over x, or 1 over v in this case. That's fine. Whatever, it's just a different variable. That's totally fine. Okay, so let me just remind you, again, the B and C are the variables, and they are temp dependent, temperature and material dependent. Okay, sorry again for all my short writing. Temperature and material dependent, and that makes this very, very accurate. Okay, this is what engineers largely use. It's insanely accurate. So almost a near perfect description of the dotted line. And these dotted lines get a lot curvier under more extreme conditions. Higher pressure when gases want to liquefy. And I'm going to show you how these lines changes when you're at like high pressure and temperature, when gases are very non-perfect, non-ideal. Okay, so this is great. And it's great for engineers because engineers have to worry about power plants exploding. If you get something wrong and you're engineering a power plant and your liquid turns to gas, everyone in that plant's going to die. All right, that's almost guaranteed, because if a large volume of liquid turns to a gas, and it would do so because it's hot, that is actually what an explosion is. You think, oh, well, that's dynamite. Dynamite is a solid that turns to hot gas very quickly. Same thing, right? Okay, so this is all fine and good. But here's what I don't care. All right, so again, it's a Taylor series expansion, a little funky because it's not x, but 1 over x or 1 over v. But I know already, I don't get anything out of this. I already know I can fit a Taylor series to anything. I can have one of my cats draw something up here, and I'm sure it'd be crazy, but if I have enough terms in the series, I can fit it. There is nothing I can't fit to a Taylor series. I already know that. I knew that before this class, or before I taught it for the first time 10 years ago. I knew that, and hopefully you knew that. So I don't get much out of this. Again, this is a great tool, but that's not a tool for learning about why. Why is this line curvy and not like 1 over x? Why is that? That's what I'm trying to get to. Okay, so I might use this thing for fodder for questions for like exams and homework, but I'm not going to do anything else with it. I do want to tell you though, and again, we're not going to do too much with the Virial. I'm going to do some other types of real gas equations, but the B and C coefficients, they are related to properties of the gas that go beyond just being parameters in an equation. I can say, well, the gas is kind of squishy, and that would actually be the B parameter. And anyway, so you get the point. I'm just not going to do that kind of stuff with this. What I can do with this is, as I mentioned before, and as you saw in your homework, I really care a lot about units. You need to be able to work with units correctly. And you're thinking, yeah, that was freshman chemistry. Yeah, but I can make it harder, and I will. Let's start doing it. All right, so, and I do have a section on the test. The first test is a section called units, where I'm going to throw some, yeah, they're just units. They're easy, but trust me, I'm going to make them a little complex because life is complex. And let me go ahead and give you some examples of that. Let's see, what can I do? The first thing I want to do is, all these real gas equations are rarely expressed this way. They're usually expressed this way in terms of not volume, but volume per mole. You're going to thank me for this. It makes everything much easier. We're about to do a lot more of real gas equations. This is going to be much easier. Just remember, like on the homework, when I have you do virial gas equation calculations, don't forget that when you see a VM, you need to take the number of moles also given in the question and divide the two and work with that. Just don't forget that. Okay, if I do that, then notice that I've just simply got, I just simply took out the n on the other side. Again, it's a little bit trivial here, but trust me, it does make things a lot easier. And that actually, remember, I took it out of the whole thing, so that affects this expansion as well. And again, I'm going to stop at the 1 over v squared term, vm squared term, sorry. Okay, so I've just thrown you this on an exam, and I'm going to ask, sorry, again, I have to kind of imagine what the camera sees, but I can do that. So what am I going to ask? Okay, I stated this last time, but it bears repeating, which is that there are two things about units. They multiply into new units. All right, that's not a hard one. That's what kilograms per meter squared divided by second squared is the joule. You've known that for a while. But they add, and subtraction is just the addition of something negative into the same. Okay, and that's the one that actually is a bit of a curveball that I think you haven't seen before. And let me go ahead and give you, okay, so I've given you this on the test, and you have these two principles, and now my next question is, what are the units of V over Vm? See, I made it kind of hard. For one, I haven't even told you what V is, other than it's a number that's temperature dependent and depends on the material, but who cares? I didn't give you any units. VM, okay, that's liters per mole. Again, I like liters. If you are a purist, it'd be meters cubed. That would be SI. Whatever. Let's just do it my way, all right? Liters per mole. B, I never even told you. I never even told you what the units are. Yeah, I know the units. See, I told you this is tricky, but it's not tricky. What are the units of V over VM? What was that? Okay, you know what I heard was that? It's kind of like a whale. Well, how about I call it some habit? All right.
Would it be liters?
The what?
Liters?
Okay, now hold on. Apply the second. Tell me why that works by the second principle. Add or subtract the same units. I'm saying add. You're right there. Why not?
Would it be liters per mole?
No. You are not applying this principle. Look at this. They add or subtract, and I'm seeing three things added. Each one is the same unit. How about you right there?
Is it moles?
Again, three things. Now, do these things have the same units? Do they have the same units?
Yes.
Yes. Okay. Pick one. Right. There we go. Now, notice I actually said pick one. That wasn't a question. It was pick one. Pick one. I'm telling you. Pick one. What are the units of the number 1? Right. No units. Okay. No units at all. Like a percentage, by the way. Percentages have no units. Even if I say percent mass, that has no units because it's mass over total mass. Kilograms over kilograms, no unit. Anyway, examples, whatever. Okay, now the thing that might have, I kind of actually would hope that thrown you off, that you had this RT that multiplies it out. That actually doesn't matter because within this bit here, there's a summation and each one must have the same units, including no units of all. Okay, now with that said, what's B? Now we can figure out what these units are. Now, B, all right, bit by bit. Same as VM, right, it's liters per mole. Right, so it cancels out the VM. There you go, perfect. Okay, now let's take care of that RT. Okay, let's do RT, VM. Sorry. RT, I'm going to go ahead and multiply it through the middle term. Okay. Now, definitely much more complicated. R, joules per K per mole. T is Kelvin, B we just figured out, BM we just figured out. Tell you what, that's going to take me a while, but instead I can look up here and get a very quick answer, real quick. Give me something. PDM, right. Right, PDM, right? So now that this is multiplied through, the thing on the right has to be the same on the left. And so that would be, again, I tend to like kilopascals, and BM would be liters per mole. Okay, but, I know that this thing also has to have the same units. All right, so notice that I did the middle term, RTB over VM. What's this term? Imagine I ask you to simplify it. So it's just RT, right? What are the units of RT? Yeah, joules per mole. Joules per mole. Joules per K mole times K. So this is joules per mole. Also, consistent with our discussion last time, pressure times volume is energy, joules. VM is per mole, so it's technically joules per mole. Okay. Anyway, last bit I want to say is that I'll give you one more example, just so you have it. C would be a liter squared per mole squared. That's quite simple. And yeah, anyway, and RT times that would actually still be joules per K mole. Yeah, anyway, so this is the kind of stuff I'm going to throw at you. There you go. This is really homework help, but you know, what really slays people on this stuff is that we're not going to really do much with the Virial, but we are going to do a lot with this thing called the van der Waals. And you already have a couple of homework questions, and I'll put one on the test like this, where you do the van der Waals equation. And the problem is that there's constants, like B and C, and van der Waals has its own constants. The constants that you find on the internet, I'm going to give you the constants you find on the internet, because that's what you're going to find. Unfortunately, one of the constants for the van der Waals equation is not standard SI. It's very difficult to find on the internet a table with the correct SI constant. So I give you the one that I found on Wikipedia, and you're going to have to manipulate that on the homework question, on the van der Waals equation. And the thing is that I'd say about 20% of you, you're going to screw that up. You're not going to do a unit conversion correctly. And to be blunt, that sucks. I'm not going to count, I never give 0 credit. You know, if you have a 10-part question and the final, part 10 isn't fully correct, I don't count them all wrong. I will grade each individual part individually, but notice, you don't get full credit. Because look, I have someone argue with me every time, well, I just made one mistake. I'm like, that's why you're not getting full credit. Right, 90%. But anyway, so my point here is, I don't mean to be a bit of a dick, but look, you're all about to graduate, and the people you're going to work for have very little tolerance, or more accurately, almost no tolerance for screw-ups when it comes to something you should not screw up. Now, if you're making some business decision, and you say the market's going to move this way here, but it went that way there, that's not a big deal. But it is a big deal if you had a memo from some company that told you that and you just completely ignored it, or you thought a meter was a yard. Right? If you do that, which Boeing and NASA did when that $100 million probe crashed into Mars, that's what they did. I guarantee you a ton of people got fired over that, because that's the kind of mistake you should not make. Units, do not make those mistakes. Just remember, you're all about to go into the workforce, and it's not really all that fun. But anyway, before I traumatize you, let me give you the equation. And this is P equals to nRT. And so we're going to divide by V. But here's where it gets a little tricky. So P equals nRT over V would be the perfect gas law. So already I don't have the perfect gas law. And it tacks on a little something extra. And another little bit right here. And now I told you that this VM deal is actually very friendly. And here, I'm going to toss this up in a second. This is how you'll see the van der Waals equation. This is really a lot easier. Okay, so again, it just, look at that. And that just, it looks easier, right? And it is. So that's why I like to stick with VM. And, okay, sorry, this board, I really don't like this classroom that much. I may try to get us out of here. Okay, let me tell you a little bit. Okay, so it's designed to deal with those wiggles, and it does it very well. Not quite as good as the Virial, and that's because the A and B parameters, they are not t-dependent. Okay, so that makes it easier, but it makes it a heck of a lot less accurate. Literally, if you, there are engineering books that have B and C Virial constants that are as a function of temperature for all gases, and they live, you sound like, oh, that sounds like a lot of data. Yeah, it's like encyclopedia big. A and B are not temperature dependent, so that's easy. And they mean something. And that's what we're going to do. Talk about what they mean. And this gave Waals a Nobel Prize. Okay. The fact that this character revamped heat equals nRT, again, if this was just equation fitting, curve fitting, it's not quite, I don't see a, that's the thing about this, I don't see a Taylor series, which again, I know fits anything if I just apply enough terms. I don't see that. So it's been designed a little bit more than brainlessly. And the A and B means simple things, which we're about to cover, and describes all these wiggles in the gas, and they gave Waals a Nobel Prize. So imagine that that's why I start with this. Okay, let me start trying to understand what this means. Okay, let me give, while I'm erasing the board, let me tell you a couple of hints on the homework. Notice up there that in all of these perfect gas equations, like the one, real gas equations, like the one on your homework, which is different than any of these, because I have to switch it up for obvious reasons, that if you get rid of the parts that are non-ideal, and you would do that by setting them equal to 0, by them I mean like the A and B of the van der Waals or the B and C of the Virial, if you set them equal to 0, you must return the ideal gas equation. It has to, or something's really, really screwed up. So that's a hint that applies to the homework, by the way. Now they also mean something, and by the way, what I'm about to do, I'm going to have you do something really similar to this on the test. All right, big heads up. Some of you woke up. So what I want to do now is figure out what A and B mean. And I'm going to do this with algebraic manipulation and taking limits. That's 90% of the derivations in this class. The parts that involve calculus I'm going to cover in the next hour, so that's why I want to stick around. Let's start with A, the A parameter. Let me rewrite the van der Waals equation. And I do thank you all for being quite quiet, by the way. That's actually really made my life easier because, again, when I hear a lot of sound, I shut down. And what I'm going to do is, so keep it up. So what I'm going to do is I've written the van der Waals equation, and I'm going to make the pressure very, very small. Right? Now, again, what I'm doing is I'm going to make limits, I'm going to do algebraic manipulations, and I'm going to figure out what A means. Now, if I make pressure small, tell me, how did I make pressure small? I got a balloon, and there's gas in it, it's atmospheric pressure. What would I do to make that pressure less than 1 atmosphere? Increase the volume. Increase the volume. Therefore, dm is big. Okay. Okay, now, curve fitting is done by engineers back in the 50s and 30s and whatnot, and they tabulated Virial coefficients and van der Waals coefficients. And let me just go ahead and tell you, if you haven't looked at the homework, the B parameter, as well as the A, but the B parameter is a very small number. So a very, very large number minus a very small number is still a very large number. So let me do this. Now notice I put a little squiggle. I actually am oddly careful. RT over VM. I'm just going to ignore the, I can't ignore this. I'm just going to ignore the B. Now, next step is recognize that this, sorry for my funky use of the board, P naught is perfect gas. Sorry, I think I've been using the term ideal gas. That's what your book used. Ideal gas pressure. Okay. Right. P is equal to RT nRT over V, which is RT over Vf. All right, so recognizing that, what I'm going to do is I'm going to say pressure minus the real, remember this is real gas pressure, this is the perfect gas pressure, is minus A over Vm squared. Now, remember that there's no such thing as negative pressures. That doesn't make sense. There's no such thing as negative volumes. And I've already said that the engineers have done a bunch of curve fitting, and we already know that we already know that B is small, and we happen to know what the A's are. A's vary a little bit more than the B's, but they're all positive. Okay, so if every gas that's ever been curve fitted to the Waals equation had a positive A, what's this? It's negative. Folks, I'm going to do this half this class. Is it positive? Is it negative? You just saw it for the first time. You're going to see it about 1,000 times more. So remember that. So here's a therefore. Now you're used to that as well. A real gas pressure is less than a perfect gas pressure. That's what I get from that. Okay. So something I've learned about gases. That real gas pressures tend to be less than a perfect gas pressure. It's not always true, actually, and I'm going to tell you a little bit about that. But most gases, the real gas pressure you measure, so I got a steel box, and there's a pressure gauge. I know the volume. It's a steel box. I know the volume really well. I filled it with nitrogen. And I know the volume, I know the temperature, and I read the pressure, and it's less than what it should have been. So expect that. Now the A parameter did it. Now I should be able to figure out what the E parameter is. And what I conclude is that gases attract. Okay, now here's what I'm thinking. Here's my balloon. Little circle. Here's a balloon. There's a little string. A little child's hand. And the child's being beaten. Oh, sorry, I'm just... So here's all these gas molecules, and remember that they ought to be hitting the wall harder than they are, right? Now what would do that? Now I can think of this like a bunch of stars in a galaxy, because it kind of looks like that. Especially remember I was talking cosmology a little bit last time. Remember next semester I am going to solve E equals mc squared. I'll show you how to do that in an extra hour. But what I'm thinking is that the gas molecules are kind of attracted to their inside, not by gravity, that we don't do gravity in this class, but by probably electrostatic attraction. Anyway, the gas molecules are not hitting the walls as hard as they should because they are actually attracted to their interior, which is composed of other gas molecules. Gas molecules are attracted to each other. And again, they want to hit the wall, but they see that they're going to leave their buddies behind, so they kind of back off a bit. That would drive the pressure less than the ideal gas equation, which assumes that molecules, I got rid of it. Recall what I said, look at your own notes. Gas molecules do not attract each other. Okay, and real gases do, and the A parameter accounts for that. So, there you go. Let me draw you a little bit how that works. Let's do HCl, which is a very non-ideal gas. And you think HCl, now you're familiar with HCl in the organic lab as hydrochloric acid. Is that a gas? No. In organic lab, well, what about, that's HCl in water. What about pure HCl? If I get, okay, here's a bucket of HCl from organic lab in water. Now I can magically remove all the water molecules. What's left?
Gas.
Yes, a gas. It is a gas. The way you make HCl in, in the chemical company, they make HCl gas, they bubble it through water. They actually have to stop. Once it gets to about 35% by weight, the gas just starts bubbling out. That's saturated. Anyway, okay, so HCl is an example of a very non-perfect gas. And if I draw it, sorry, I should be drawing this a bit bigger. You see what it can do? It can do stuff like this. So, I don't know if I'm doing these radii correct, but what I'm seeing here is that I know this sucker is very polar, and if you line it up just right, opposites attract, not in real life, but gas molecules, and so that works, right? They like that. They're attracted to each other. Here's another way. I call this the dog interaction. So I got HCl, trying to draw them the same way, so I do it sort of So small, I call this a doggy interaction. You know why? Because they're smelling each other's butt. Dogs, I live over in University Village, and there's nothing but dogs smelling each other's butts. They're going after squirrels. But, yeah, so these things are very attractive, right? Dipoles line up. Now here's another little thing, and don't write this down, by the way. So yeah, I see. Yeah, these guys definitely can line up the right way. They definitely attract each other. That's why there's an A parameter and it drives the real gas pressure down. Note though that for every configuration that's good, I can make one that's bad. So it seems like the effects ought to cancel out. Actually, there's a reason they don't. It's if two things can attract each other, they will. Now again, if I had flipped this the other way, or same here, in an equal configuration, they would have been repulsive by the same amount that they're attracted. It seems like they should cancel. Reality is, if two things can attract each other, they will. They will rearrange. They will rearrange from the negative, unfavorable interactions to the positive. They will do that. Why? Because in the process, they'll release heat. And that is actually going to increase entropy, and entropy always increases. That's the second law. Now, don't write this down. I'm just previewing, because we're going to do the second law in this class. The reason that things attract, if they can, they will reconfigure, because that will maximize entropy. So that's why that happens. Anyway, now HCl is very unusual. What about something like xenon? That is, xenon does not have a permanent dipole, right? Noble gases. I'm just using xenon as an example. What xenon can do is this. It has a nucleus. It has electrons. And as much as your freshman chemistry textbook drew these orbitals, s orbitals and whatnot, especially s orbitals as round, reality is if you can stop time, the electrons are somewhere. And the nucleus is definitely somewhere. That's the easy part because it's so heavy. But if I can stop time, the electron is truly somewhere. So notice that this is actually complete analog. This and this are actually almost identical. Now, reality is this electron swings that way, and this electron swings that way. It does so impossibly quickly, but for a moment it was okay. And again, if it can arrange itself in a way to be happy, it will do it. So, sorry, I should have put it, my bad. So this is xenon or helium or yeah, anyway, blah, 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 noble gases. And this is a dispersive. Okay, dispersive interaction. Also called London forces, and by the way, you don't know this yet, but you will. I don't require you to remember first test. I better remember that a London force is a dispersive force, and that blah blah. No, you don't. Okay. Maybe this picture, yeah, kind of. But again, is this hard to remember? I contend you don't even really need to try to remember that. You just got to remember basic things. Okay. So now, what else do I want to do? I've been really running my mouth badly. I need to do the B parameter. A is not really, when we start with A, it's not really that interesting. And that little proof I just did for the A being attractive is a little lame. B is cool. Straight ties are cool. Who got that reference? No one? Doctor Who. Matt Smith, you suck. Anyway, I haven't watched Doctor Who since the new guy took over, actually. So don't tell me what happened to Matt Smith. I'm assuming he's still alive. I'm not kidding. He's watching Game of Thrones. I'm Toman. Anyway, God, I could not believe the last episode. Like, I was so annoyed by all the music and stuff, and then I realized that you were seeing how everyone was getting set up by Kersey. That was, anyway, all right, sorry. Let's do B. Sorry, I'm going to talk a lot about Game of Thrones and my cat Zoe and Charlie, by the way. Okay, let me start again with the Waals equation. And at this point I have it, I'm going to put it on my gravestone because I have it memorized. Okay, so I want to get to the B parameter, and so I'm going to want to try to put like B is equal to yada yada yada, and I'm going to apply some limits. I just did that, and hopefully you can do that. But now I got to get B to one side, right? Like right here, this is like mathematically isolated. So what I'm going to do is multiply by Bm minus B. So I'm just telling you what I'm doing. You don't need to write that down. I just don't want you to get confused. So PDM minus B is equal to RT. Okay, and now this is where, if this is on a test, you screw up, you're going to forget to do it here. I have not been so uncareful as to not do this on a test. It's very proof. I'm probably going to, of course, give a slightly different variation of this proof on a test. So again, I just multiplied everything by VM minus B. What people tend to do wrong is forget that that term's there. Okay, now what I want to do is I want to factor the VM minus B, so I'm going to bring this term over. I'm going to do 2 steps of algebra, and I hope that you can do this on your own. So, because if you have some trouble with algebra, I'm not trying to make fun of you, that's just not good. You should be able to do what I'm doing in 2 steps. And again, I'm sorry, just for convenience sake, I'm just going to go ahead and do them. Okay, now I've got this. And I'm sorry for the sake of readability on the video, let me just move over here. And so what I've got is, it has RT. What I'm going to do is divide by that P plus A over VM squared. And, okay, so that leaves VM minus B on the left, so I am going to put B on the right, and then that leaves a VM here. There we go. Sorry, that's not pretty. I don't like that anyway. So there you go. All right, now what I've got is I've got B by itself, and that's what I want. And so now, remember I said I need to apply a limit, and I haven't done that. Looks like now is a good point. And what I'll do is, instead of working with very low pressure, I'm going to work at high pressure. So A parameter, I make pressure low, and the B parameter, I make pressure very high. And of course, B will be very low. So I have to compress the thing to do that, and so I do that. Now what I have is, okay, now here's the thing. I don't want you getting in a mental conundrum. Thought experiments. This is how Einstein won a Nobel Prize. How Einstein proved E equals mc squared, which you're going to do next semester. If I pressurize this system, when I manipulate equations, I can correspond that to an action. I pressurize the gas, right? So this number gets very big, but is that number going to get big too? If I pressurize the gas, and now remember extremes, I pressurize the gas an unbelievable amount. Does this change? You think? I would imagine the temperature would increase for the most part. Some gases actually won't, but anyway, we're getting there. For the most part, yeah, if I really do this and I pressurize a gas to an unbelievable extent, it actually will get hot. It's in a metal box. What happens next? What I say about metal boxes that are not wrapped in glass wool, they're going to not explode. It's Captain America vibranium. Yes, I know about vibranium. Okay, it got hot, but it did what? What? I'm sorry, my deafness is getting in. It cools back down. Okay, here's my point. This can stay still. This can go up, right? If that happens, what happens to this term?
Goes up.
Right, goes to 0. Let's make it 0. So now remember, that means that the pressure is really freaking high. Now remember, A over a really small number, because V got small, is also a really big number. Okay, I got a big number plus a bigger number by a number that I can make I can actually cool it if I need to. I can make this small. I can make this arbitrarily large, I can make that arbitrarily small. This is now 0, but I do have to pressurize it a heck of a lot. In that case, that term is gone, and Vm is equal to B. All right, now I'm going to ask you, what is B equal to? Let me figure out what the units are. What are the units of B? It's very easy. Liters per mole. Okay, and I didn't need to apply, you see? Term. Now remember that these are actually added. You probably don't see that, but here's what I can do. Vm minus RT over P plus blah, 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 minus B equals to 0, right? They are actually added together, even if they're on the opposite sides of an equal sign. So I could have figured out there that this And oh, by the way, what are the units of this? Liters over mole. Liters over mole, right. So I can figure out this is liters over mole. Now I have, it's a volume. It's not worried about the per mole. It's a volume. It's the volume of a gas if the pressure is shockingly high. Remember, I pressurize this to an unbelievable extent. What happens to a gas when I pressurize it to an unbelievable extent? It turns to a liquid. Now what happens if I pressurize a liquid? It turns to a solid. What's the volume of a solid? Why does a solid have volume? What's it composed of? The molecules. It's the volume of the volume of the molecules. V is the volume of a molecule. There you go. See, that's what he figured out. I think that's so cool. I don't do that. Anyway, so, yeah, that's what he figured out, and it's true. And on your homework, actually it's on the next homework, you're actually going to figure out how to relate the two. What you have to do is you got to remember that if you actually, what I've done is I've given you some real data, not just data that I made work. I gave you some real data on gas molecules. And what you have to do is you take the B parameter. When you think of matrix of say xenon, you got to remember that there's space in between. So when you calculate the volume from real data and you subtract the space out in between, you're going to find that that's actually almost equal to the B parameter. That's on next homework. So yeah, it works. It's kind of cool. Now, last bit I want to go over, and then we're going to take ourselves a little bit of a break. Is let me tell you about how things hit each other. Now, A is how things attract. Remember, ideal or perfect gases don't attract, but real gases do. That's the A parameter. And I understand that. B is they have volume. And remember that ideal or perfect gases do not have volume. Now, I said that in the first thing I said in this lecture. All right, now that means that they can't collide. Right? If they don't have volume, then they don't collide with each other. So B, the fact that gases have volume means that they hit each other. And that's, and again, that's why I have volumes, right? That's actually the source of volume. So let me show you how things interact. This is, I'm going to call this energy. I actually should give it the letter U, which we're going to figure out actually in about a week. And let's look at two things interacting. Now, I happen to know that the A parameter, when things get close, I'm just call this 0. When things get close, energy goes down, and that's because dipoles line up. Energy going down is good. Let's think of it that way. Energy going down is good. These are dipoles interacting or induced dipole, which are dispersive, which are London forces. Okay, and but we have this B parameter, and that does this. You can only do it so far, right? Now dipoles like to get up next to other dipoles, but everything has volume, and you can't violate someone else's airspace. And the net total interaction potential between atoms looks something like this. Okay, this is called the Lennard-Jones potential. Don't worry about that. Some people try to have you memorize that, but anyway, it's all along. Let me tell you where the effective volume comes from, right? Because you know that things, I can't walk through a wall. You know that things have volume. Now, again, remember that a minute ago when I was drawing this little xenon, I'm drawing this in the happy configuration. But what happens, the reason that things have volume is that these electrons, which were sniffing each other's butt, and they actually liked that at one point, the problem is that the B parameter, the reason that things have volume, the reason that they can crash into each other, is that this electron is getting in that electron's space. Now, you're going to learn in 344 in quantum mechanics, there's this thing called an exchange potential. Don't write this down. Right? This is preview of 344. What this is this electron is starting to occupy the same state as that electron. Okay, you remember your Alfdal principle from freshman, the build-up principle? Remember when you had metal atomic levels and you had to add electron, 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 electron? Remember that? Every electron had to have its own state. What's happening is this electron is violating that. This electron state is becoming that electron's state, and that can't happen. Again, remember, that's why when you had atomic levels, that's why you added electrons in a certain order. that principle is now being violated, and there's an energetic cost to that. That is the source of volume that you spent your whole life, you felt this your whole life, and you never knew why. And then I asked you, why do things bump into each other? And you'd say, well, just because. And that's enough. So, okay, with that said, let me just tell you that we are going to cover, I'll tell you what, let me do this because we do have the next hour. Let me show you a trend. Sorry, let me just go over 5 minutes and then we'll start 5 minutes on the next hour late. Sorry about that. I ran my mouth too long and I'm going to go quick. Now remember, hey, you know what, don't even write this down, watch the video. I'm not going to have this on an exam, so sorry about this. I should have talked a little bit less about Game of Thrones. And, well, I could have set up the video on time. So anyway, I mentioned to you that these B parameters are very, very small, and now you're seeing them, and these are very, very small numbers. You do need to think about the units because that can, scale things. But no, these are small numbers. And now what I'm seeing though, as molecules become larger and more polarizable, more fuzzy, right? Remember that these guys only interact with each other through polarization. Well, this one too, it doesn't have a dipole moment. I see that as a molecule gets bigger, more polarizable, the B parameter is increasing. And so that makes sense. So, sorry, I'm kind of going a little too fast. B parameter, I said they're attracting, so I'm talking about the B parameter. I should be talking about the size of the atom, my bad. Helium is smaller than argon, it's smaller than krypton, it's just smaller than, what's that, ethene? Ethene, right? That's smaller than ethene. So you see that the B parameter increases with size. Now, I'm not going to give a table for this one. Let me give you the melting temperature. And I'm actually going to stick with the same gases. Actually, I'll switch one of them out. I'm going to look at the melting temperature as a function of the A parameter. Sorry, again, I'm going a little too fast. And if this is 0, this is about 273. Of course, this is in Kelvin. Again, I apologize for going too fast. And I also, I do tend to draw data in class as opposed to PowerPoint. What you find is that the A parameter and that was just a screw up. You find that if you plot the A parameter and a substance's melting temperature, it forms a perfect line. The bottom line is helium, then I got argon, then I've got krypton. And again, sorry, actually I want to use water. That's a little bit more relevant to violence, right? Okay, so again, the B parameter increases with size. The A parameter increases with melting temperature, or more accurately, melting temperature increases with A parameter. I know things melt due to interaction or lack of interaction. So again, this proves that the B is related to size. A is related to how strongly you interact. So, sorry, I went over 5 minutes.